Now we were gonna do like a panel with the JuliaGPU developers, like broadly defined. So if Andre, if you want to leave, like of course I can't stop you from leaving, but if you would like to stay and be part of the panel, you're welcome to as well. Similarly, like I don't know if Tim wants to get up, you don't have to, or Julian also, since you also developed that, or anyone who considers themselves a GPU contributor. It's like very ecumenical here, I guess. I'm also gonna post if you're in the pound GPU channel on Julia Slack. I made a little hack MD that hopefully everyone can edit. Please tell me if you can't see and edit it. And that way we can like gather some notes from what everyone thinks. The other thing, just as people are leaving, we do have the closing ceremony at 4:10 p.m. in David Lawrence 121. So please go there. We'll be giving out the community awards. So after this, we'll head over to David Lawrence. Wow, that took me like 5 tries to say David. Anyway, yeah. Developers, please come up and I'll try and connect to the projector again. Yeah, so we're trying to do this panel style. So I guess like the goal here was to hear like your feedback about the Julia GPU ecosystem, like requests, things that people like, things that people wish they had, things that everyone thinks is incredible and amazing. So just go crazy with it while I hook up my display.
Some of us says. And not president. I'm guessing we should start with all of us. Question from a second ago about the integration with Reactant. I think that all remains to be seen because it's a separate array type, it's a separate infrastructure, it's MLIR based, not LLVM based. So it's a completely different way of tackling things, and it really remains to be seen how widely applicable Reactant will be. Will it be? Will it just work out of the box with all of the existing GPU codes that we have, or will there still be a role for a GPU arrays based stuff? I presume there will be. So figuring out where that boundary is I think the first step before deciding or figuring out how to compose both approaches to GPU computing. So remains to be seen at this point.
You can stay down there.
We just have that one. So here, I can also move this.
That's fine. I just basically wanted to say thank you, because when I show Julia to people or try to convince people that Julia might be a good idea, just being able to demonstrate that, oh, by the way, this broadcast, you just change the array type and then it runs on a GPU. Or like, I work with a young master student and she has the likelihood, and she's not that deep into computing yet, but she's getting there. But just going on a GPU was so easy. And now she's just in generally what this GPU availability for the language has done. Just thank you.
Yay. We're gonna wrap it.
Oh, nice.
Okay, yeah, we can pass this around. Also, as you can see, I'm taking notes, and hopefully everyone has access to this. So if I quoted you wrong, please just edit what I wrote down as notes for what you said.
Nice. Okay.
I have a in-ecosystem question and like a intra-ecosystem question. I'll ask the intra-ecosystem question first. With the added new Julia C static compilation, how do we envision where people might want to compile a workload that depends on GPU? Let's just assume that they know exactly everything about the platform they're going to run their code, but that involves GPU. Is that beyond horizon?
Not right. Well, okay. Compiling the GPU stack with Julia C is currently not an option because of the limitations that Julia C imposes. Everything has to be fully statically compilable, which is completely fine for the GPU kernels themselves, which have to be statically compiled. But the whole runtime surrounding it, i.e. CUDA.jl itself or GPU arrays.jl itself, those are chock full with dynamic dispatches in places that don't matter because it's not the hot part of the code. So having to optimize all that to fit the standards of Julia C is not going to happen soon-ish. I'm guessing at some point maybe Julia C itself is still in heavy development, so there might be the requirements of code might be relaxed from the Julia C side as well, at which point it might be more feasible to make the GPU stack statically compilable. Yeah.
My understanding is if you use the unsafe, it's possible to give it a workload where it would just compile everything the workload hits. Would that at least be a technically workable?
I haven't experimented with it myself, but kernel launches and the way we integrate, it does have some inherent dynamic dispatches in there, which I don't think you can just compile and trace away. But I should have to test it myself. I don't have experience with it. In any case, I mean, we at this point, we even still have some issues with regular pre-compilation workloads. So I'm guessing that might be the first step to tackle before jumping onto the full, let's generate a binary out of the whole GPU stack approach.
So we had to cut off the Trixie CUDA talk earlier, but I know the speaker had some feedback for the developers, so maybe we could talk about that now, since there seemed to be a lot. I don't know if you want to like put it up on the screen or just tell us what it was, or. Yeah, we can quickly show the screen and then swap back and forth. We'll make this work somehow. This is like if you've ever had to use multiple devices in CUDA, like this is exactly how painful it is. So we're really making it work here, folks. How many core developers does it take to switch display sources for a talk? Okay, we're good. We got it. Is this showing up? Yes. Okay, you're on the screen. Guessing not.
Yeah, we can go by tools.
Aha, here we go. Beautiful. This is what we were hoping for.
Yeah. I think the CUDA is not most powerful for its ecosystem, and I found that CUDA.j are quite good doing something about like package support, like it wrapped functions in QBLAS and QFFT, QSolver, and so on. And here I may think I need some support from like for our users, like we can choose the standard math functions or between the intrinsic functions. Like we can see the reference like in CUDA. Basically, it offers two kinds of mathematical functions. The first one is standard functions. The second is intrinsic functions. I guess in CUDA.j we are default to use standard functions, right? Yeah. So I hope you can offer some support, like we can choose the intrinsic functions.
Is choosing between the flip or Julia base implementation. Yeah, that's right. The light here. Yeah, use the mic. Yeah.
Wait, yeah, here you go.
Okay. Sorry.
Yeah, I guess the point being made is like being able to choose for, say, if you do x divided by y, which function does that actually call? Does that call the implementation in LLVM if you just emit a div instruction in LLVM, or is it calling something in libdevice provided by NVIDIA? Is there the opportunity to actually like change that? And I know there are issues with semantics around one implementation providing certain semantics, another providing other ones. So Tim knows more about this.
Yeah, so in general, we always try to pick functions such that we respect Julia's semantics. So especially with respect to floating point semantics, NAND propagation, and so on. We start out by trying to use NVIDIA's functionality from libdevice, for example. But when we notice that there's disagreements between the semantics that Julia typically has for its standard library functions and what is being provided by the NVIDIA standard library, we move away from the libdevice functionality to custom functionality, such that we think it's more important, or at least the reasoning is that it's more important that you can compose or port existing code to the GPU and have it execute correctly, rather than get 100% of the performance out of the device that's available. Making that configurable is non-trivial, and I'm not sure it's worth it. But I mean, users, please correct me if I'm wrong. But so the trade-off is performance versus correctness, and up until this point, it has been mostly on the correctness area, making it easier to port code rather than making it easier to extract all performance.
How much performance do you think that? In the market.
So the note was how much performance is missing. I think that heavily depends on the kind of application. Most of the time, 0, because GPUs are exceptionally good at hiding the performance of additional arithmetic operations anyway, and hiding it behind some memory load that needs to happen anyway. But if you have a kernel where you're bottlenecked on arithmetic, and then switching from the high performance intrinsics to a slightly lower performance one may have an impact, but I wouldn't dare to say what percentage of difference that would make. Highly depends on the kernel. And to some extent, we already have a minor version of configurability, and that's by using fastmath. So we do implement the fastmath versions of math intrinsics. The problem is that this is a fairly crude tool just because of how it's implemented in Julia itself. It's a purely syntactical transformation by sticking at fastmath around a certain block of code, whereas that could be something more fine-grained at the compiler's level. But that would first need to be something that would have to be implemented in base, I would rather guess, than bolting it onto the GPU stack as some custom functionality.
Would you have any examples of, well, with fastmath, you have the checked versions and the unchecked versions. Any other examples of where this kind of fine-grained...
But all of the math intrinsics, every trigonometric function has a fastmath equivalent. That's not necessarily checked unchecked, but it does dispatch to lower precision functions with a higher rate of error. That, for example, in the case of some GPUs do actually have a coprocessor which can execute certain high-level math functionality. Generally, we do not dispatch to them because they're wildly imprecise, especially compared to what Julia math functionality delivers out of the box. But with fast math, we do dispatch to those, so that can make a difference.
Thank you.
Also, you had a couple more things you wanted to. Oh.
Yeah, and also like we can support. I hope you can support more types. Like here, so like CUDA, C++, they provide some vector types. Like I found the flow 4 is super useful, so I can. But this is not a big problem for me. So if I want to use them, I can make a PR to like contribute to CUDA.jl. What I found is really problematic is the tool ecosystem. I find that JuliaGPU are kind of running behind, like it's not matched so well with the CUDA tools ecosystem. Like I can take a quick example. Oh, sorry, don't know this one. Like if I want to provide this really complicated kernels, and I try to run this session is already attached by the inside compute. So let's say this is doing the profiling. It takes some time. And this is the kernel we want to look at. Like here, the inside compute gives some suggestions. Like we can just ignore the first suggestion because I'm mainly running on double precision, and it suggests me to use the single precision. What the main problem is the uncoalesced shared memory access. Can you see it clearly?
It's a little small, but
Yeah, but it suggests me there is some problem in the shared memory access. So we go to this kernel and check this, and see here the memory server is really bad. So there must be some problem with our shared memory accessing. So then I check the source code. Let's see, we look at the assembly code, and we can just search for something like, let's say, LDS. And I will explain what is LDS. LD means load memory, and S means shared memory. So we mainly have to, if there is some problem with our shared memory accessing pattern, we mainly have to search. If we want to locate it in our assembly code, we mainly have to search for LDS or STS. STS means store some memory to the shared memory. So if we search LDS and it helps us locate something like, here we can see some warning signs, and it indicates that there's some problem with these lines of assembly code. So next I want to do is to map this, locate which line of source code is actually have the problem. So if we locate this one, it's all mapped to something
that's no deficiency.
Yeah.
That's no issue in LLVM, and we've asked NVIDIA to help us about that. But that's a known issue.
Yeah, and this problem has troubled me for a really, really long time. And if we actually look at the real code or real custom kernels, it shows nothing about the problems. Like it's all showing some branching problems, and I cannot locate the problem in my code.
Yeah, it's a known issue. And for some context, the reason is that Julia relies heavily on inlining, whereas the debug information is only attached to the innermost frame. So that means that if you have a kernel that, for example, does array indexing is expensive. All of the frames will be attached to the implementation of getIndex and not of the caller frame, which calls getIndex. That's because, again, everything is highly sensitive on inlining. The debug info does retain all of the frames where the code comes from and how it was inlined, but that's not retained in the generated PTX assembly, even though PTX does support that. So we're in touch with NVIDIA to try and add that functionality to the MVPTX backend, such that tools can ingest all of the information regarding inlining and more correctly allow attributing the cost of certain operations in tools such like Insight Compute.
Awesome.
I just hope we can get more support from the toy cases.
Yeah, I think that would be very helpful. I just want to also keep us aware of time because we've got about 10 minutes left, and I think all of us could probably discuss LLVM support all day, but it would also be great to hear from the wider ecosystem of people who are here and maybe aren't all CUDA users. So if you have folks in the audience who have a question.
Did you have one also? Okay. First.
Just concerning what was talked about before about the types that were supported. So for indexing, int32 is only partially supported still, right? Is that on the horizon to support that anytime soon, fully?
There wasn't anything keeping the PR back, so it just needs somebody to finish it up and make sure that it passes all tests. It should be relatively straightforward work, or at least insofar that we tackle the problem from within CUDA.jl. Julia itself supporting 32-bit indexing is probably not going to happen. That is a very, very large change to machinery that very few people fully understand. So it's going to be tricky to make sure that Julia itself can properly perform 32-bit indexing, but with sufficient overrides, we can do a fairly good job from within CUDA.jl itself. And you know which prototype PR I'm talking about. And at this point, it just needs somebody to go in, run the test suite, see where the failures come from, and debug as appropriate. But in principle, there's nothing holding it back.
Okay, thanks.
Sorry, I have got a question on that. What exactly do you mean by supporting the 32-bit integer indexing in that level? Do you mean like having the integer literals that you write for indexing, say array brackets 1, that 1 not being a 64-bit integer as it is in Julia by default?
Yes, and the problem is that we rely on functionality from base. So if you call getIndex, there's multiple layers of indexing in between you providing a literal to the square brackets and it's calling the innermost getIndex call and making sure that the 32-bitness of the integer is preserved all the way through. That is something tricky that in Julia is difficult because we generally use the machine native int type in all of these definitions. Expanding that to the full integer type, which can be any kind of integer, opens up the core to lots of potential ambiguities, and that would be a fairly tricky change to get into base. We've worked around that by sufficiently re-implementing enough of the indexing stack in CUDA.jl itself as such to preserve the type of the literal that you provide to the square brackets. But there are still corner cases where that will not work. For example, when using views or when using derived array types, we may still rely on certain indexing functionality from base. It's only specialized for the CUDA device array type.
Thank you.
Do we have another audience question? Can you guys raise your hands a little higher? Sorry, I think it can be hard to see. Okay, there's another one there.
Yeah, I wanted to ask what's the state of OneAPI.jl? It's apparently it's looking for maintenance, so this could be a good way to find some.
OneAPI.jl is in a tricky spot because of multiple things. Primarily, Intel not doing all that well right now. And they funded the development of me working on the backend. So that funding has disappeared, meaning that I have to spend my time equally on OneAPI as well as the other backends based on the amount of users. And OneAPI has very few users, sadly. It's definitely not unmaintained, so it's still part of CI. It's still being tested as a reverse CI in some of the in GPU compiler, GPU arrays, and so on and so forth. But it's definitely on the low end scale of developer maintenance, as at least from my side. I mean, the community is happy to take it up and continue some of the work there. But from my side, I'm not investing as much time anymore as I was last year. Similarly, I guess it's also waiting to see what Intel is going to do about OneAPI stack itself, which is why I'm also not putting too much effort in it, even especially if maybe OpenCL may end again up the way to program Intel GPUs in the future. So that's all remain to be seen, and that kind of uncertainty puts it in a slightly tricky position.
Related, where should a more advanced user, let's say, contribute to harmonize these different capabilities of backend? Because right now we are running into a problem where Metal does not have Atomic's floating point addition onto their shared memory, so which means we probably want a different lowering to a cast loop in Atomics, but it's not clear to us, even if we want and have the capability to make the contribution, where and how that should happen.
The answer to the first half of your question was easy. That's porting stuff to GPU-arrays.jl, but support for Atomics is something very low level that needs to happen in the backends themselves. For Atomics specifically, there's two possible routes that we're exploring. The one is continuing with the current approach of abstracting functionality in atomics.jl and unsafe atomics. which is one of the packages that was developed as a common base of atomic functionality. We could put, or there could be put some functionality there that specializes based on the backend as to dispatch to then either compare and swap loop or a native implementation. It currently does not have that functionality, so it's always going to try and dispatch to the, for example, atomic add function, even though it might not be supported for certain types. That's problematic, so the quick fix would be to make atomics.jl smarter. The long-term fix, we think, is try to rely more on LLVM atomics and then legalize them as part of the pass in GPU compiler, such that all of the backends are just going to emit plain atomic operations. Ideally, that also makes it possible to reuse some of the atomic functionality from base itself. So plain LLVM IR atomics, and then a post-processing pass in GPU compiler that legalizes based on which device supports what. That is the current approach, but the current reasoning, but that takes a significant amount of work to materialize. There is a prototype PR for half of that on GPU compiler itself for Metal. So if you're interested, you could take a look at that, or we could discuss what potential follow-up work could be done there by other people interested in this. Of course, the more easier fix is just to make your kernel device specific and to use atomic from the backend itself, where currently those smarts should already have been implemented.
So we probably got time for one more question, and then people can maybe find us later or at the hackathon. There is one more question. Anybody? All right, there's one.
I'm aware that a few years ago there were issues with pre-compiling GPU kernels, but I haven't really kept up with the state of that. Is that fixed now? Like, can I? Okay.
Yeah, there is a bug in Julia itself that prevents us currently from accurately pre-compiling GPU code. The issue is that code is being cached when it's compiled, for example, to emit in a precompilation file, but the CPU caches and the GPU caches should be fully disjoint because we call into, for example, LLVM intrinsics that are not supported by the CPU and vice versa. And currently there is a leak somewhere. So GPU code is leaking in the CPU cache, preventing us from precompiling GPU kernels because it might break your session. That is something that needs to be fixed in base. Once that's done, we assume that a simple precompile workload should work to precompile all of CUDA.jl. In fact, Valentin has tested it in the past, and it has worked perfectly fine. So we just need to fix one remaining bug in Julia, and we're getting close, in other words. Thanks.
Cool. Okay, with that, and considering we all have to pack up, let's wrap it up. Thanks to all of our speakers. Thanks to everyone who came to the GPU Mini. Thanks to our awesome AV tech who put up with a lot from us. And let's all head back over to David Lawrence 121, aka the main stage room, for the closing ceremony.